that. So this idea of, you know, the neural assembly being an attractor landscape was greatly influenced by Freeman's meeting of Ilya Prigogine at Solvay Institute in Brussels. Freeman was there for a year, I think, as an honorary chair of some kind, and gave, you know, a lecture on what do you call when an invited chair gives a plenary lecture? Is there anyway? It was at Brussels that he met Prigogine and was influenced by Prigogine's ideas about self-organizing dynamics in chemical and thermodynamic systems. And Prigogine had a number of criteria, which I'm not going to bring up here, but Freeman, in his work, repeatedly points out how the properties of neural systems fulfill Prigogine's criteria for self-organizing dynamic systems. So, the patterns again here, these examples are from, on the left, there's a set of trials for air and the banana oil, I believe, is the amyl acetate stimulus. And then on the right is the same pair of stimuli after consolidation. So this is a reinforced stimulus, and then the same, the same stimulus was applied after consolidation has taken place. And the pattern is changed, even though the behavior, you know, is the same.
Okay, so this is a topographic map based on the 64 points that are both. So was it one of the cortex? There was a map on the cortex as well as on the olfactory bulb?
Yeah, he did recordings at both places at different times, but I think these are prepiriform cortex.
Okay.
He saw the same phenomenon happen in the bulb as in the cortex. And he, go ahead.
Say how it is that we get from the 8x8 pattern of electrodes to this map.
Okay.
This topographic map.
So you're familiar with how topographic maps work in a geographical context? That what the lines represent?
Well, they may represent something like altitude, for example.
Yes, that's the geographic context.
Yeah.
So each line is an equal altitude. And in an electrical setting.
So each one of these lines. No.
Let me finish. In an electrical setting, the lines represent equal electrical potential.
Uh-huh.
So equal voltage.
Equal voltage between what and what?
Well, there's a reference electrode.
No, in the geographical thing, you've got a location.
You've got a line across a location.
You've got a line and a location.
That's right.
What do you have here instead of location?
You have location.
Oh, you still have location.
Yes, you have an 8x8 grid over the cortical surface.
So they just do an 8x8 plot and then build
Do
that thing
smoothing.
into.
Do smoothing and averaging to extrapolate, to interpolate.
I got it.
Okay. And so each one of those lines, and later on, actually, I could break out now and show you what he did when the technology got better.
Would it be the electrical potential or the amplitude of the?
Yes, the amplitude is an electrical potential. It's measured in millivolts.
Yeah, because that one image should represent the image that you showed before. I mean, if
yes, and each one of those little traces is a voltage with time.
Right. So that's with time, and this is not representing any time information. So I'm wondering, like.
That's right. This is a snapshot at one moment in time.
Okay.
Yeah.
Oh, okay.
Yes.
That's
right. Good point, because that little trail that had that many
Yeah.
would show well, you can do it for different time scales, but, you know, I mean, you could do it instantaneously, or you could average over tiny bins. He did all kinds of stuff. I don't know. No, but this is a similar plot on the left there, with a color indicating altitude, if you will, or electrical potential, with the and then he has a 3D version on the right, with the dark blue being the lowest, and the red. There's a color scale right there to the right of that first figure. So this is all derived from the same 8x8 array. Okay, so we're back here. So
what's the difference between the one on the left and the one on the right? This is 3 days later.
I think
Three days
yeah.
later, and he's presented.
it's
the same.
trial set 3. I don't know how many days later it is.
Some days later, yeah.
Yes.
I got it. Some days later, but he's presenting the animal with the same stimulus.
Yes.
But of course, it's hitting different cells in the mucosa. So
Right, but I mean, he can do he can do repeated trials on the same day, and it's still also hitting different cells.
absolutely, but you don't get this kind of difference.
That's right, and he said this is consistent. The time scales are consistent with those necessary for consolidation of the memory.
Consolidation.
Yes, and so
Steve, what's confusing me a little bit is the air. So that's sort of the neutral stimulus, right?
Yeah.
And air is responding in a somewhat similar pattern, or at least has some similarity to the banana oil or whatever you were talking about. So
what do you mean?
So I'm looking at on the right side. So on the left side, both the air, the neutral stimulus, and the banana oil, the pattern is changed on the right.
You're trying to visually conclude something from whether they're different or whether they're similar.
Well, I'm looking at air and then the one right below it on the right side.
I would say that the classifier algorithm is able to distinguish these two accurately. Yeah. I don't know visually if I could. If you showed me one and the other and didn't label them, I wouldn't know which was air and which was amyl. They're not significantly different enough for me to be able to classify them.
Right. I mean, on the left side, I agree. On the right side, it seems that both of them have a change in the topographic map.
Oh, that point, yes, absolutely, and that we'll get down to here in the bullets. That's a very good point. The air is also different 3 days later, and these bullets I think are gonna speak to that.
Okay, great.
So he says that this pattern is not a transcription or representation of the stimulus, because the same stimulus will have different patterns on different days without the behavioral. The animal is recognizing the stimulus behaviorally in the same way. The pattern is different. So we don't have this isn't determined by the stimulus. It's a process. The pattern is created by the bulb in response to the stimulus. So, and if you do the same stimulus, not just on a different day, but in a different context, like for instance, you have a reinforced stimulus that got a reward. Now you switch the reward to a different stimulus. Well, the pattern for the first stimulus changes. Or if you flip it to a punishment instead of a reward.
Or even if you learn some new one.
That's right. Any new patterns created, all the existing patterns change.
Yes.
So they're all connected. The memory is synaptic and structural. He is able to put this in the same context that all the other theories of neural function, operate on. It's synaptic learning. But the remembering itself, the access of the memory, is a dynamical operation. You never get the same thing. The bulb creates a pattern that is triggered by the stimulus and influenced by the memory and the current state of the bulb and other things of the animal. And it's very much, so what's happening in this data, I think, and I'm jumping ahead a little bit here, but I think it's very similar. There's many pieces of what goes on in an entire LIDA cycle happening here in a sensory area. Now, our model would still break it up into different modules, but in the brain is using this area to do those operations. You know, it's not just, I think Freeman's view would say the sensory activity propagates dynamically to the other parts of the brain, but it doesn't send a message encoding the stimulus to other parts of the brain. You know, or at least not in the way that the 88 BBS paper is very anti-representationalist. He does.
But that's what he's saying here.
Yes.
This is not, you see, I can still think of this as being representation.
Yes.
But it's not the typical representation that
Not
you use in
a
computer science.
representationalist representation.
Yes.
Yeah.
Exactly, it's a representation in terms of attractors and that kind of thing.
Yes, and
If you want to
Freeman,
use that term, he'd prefer not to use the term.
well, he does sometimes use the term in reference to what brains do or what minds do. And it's unclear to me, and I still am reading How Brains Make Up Their Mind. He talks very specifically about the brain making representations, but there's something that's not well parsed anywhere that I've seen. Maybe I should consult Stanford Encyclopedia of Philosophy to see what they say about it, but the idea of what representation means, I think it has different meanings in different contexts. In the representationalist debate, it means something very specific that is more related to kind of like zeros and ones encoding, you know.
This is not that kind of thing at all.
Yes. And now there are many neuroscientists, mainstream neuroscientists, who think in such information processing terms. Freeman doesn't deny the information processing that happens in the sensory areas. He just denies that it's the basis for everything else that happens, that it's like a digital computer. He says it's the gateway into a dynamics. That's what happens at the microscopic level with the individual cells, but there's a dynamic that takes place on top of that, like all the metronomes together having a synchronous state. You know, even though each one has got its own little spring and its own little, you know, thing driving its frequency. Okay. All right. Now, this is a little tricky. I hope this doesn't take us into a... Okay, so when Freeman saw this in the data, that these wave packets emerged, his intuition regarding dynamics goes, okay, there's a kind of a chaotic background state. The stimulus kind of goes into this, you know, drives it into this organized state. But this repeats every time the animal sniffs. And in between, it goes back into the background state. So what's happening here?
Chaotic state, yeah.
Yes, and so...
What kind of criticality?
Self-organized
Yeah.
criticality, or self-organizing criticality.
Yeah.
Yes, and that's his intuition here, but he's like, how is this happening? What's going on to, you know, make one pattern go away and it goes back, and then it's primed for the next pattern? What's happening? And so he and Robert Kosma and Joshua Davis, remember Joshua? Remember from Orlando?
Oh, yeah.
They have been looking at this data and other data from other parts of the rabbit sensory system, and analyzing it with modern computers and Hilbert transforms. He began using Hilbert transforms. And there's wavelets. There's all kinds of new mathematical approaches to looking at what's happening in this data. he found, using the more advanced math, something called a null spike in the activity. And that's what I showed you over here when we went there. This is the activity at a particular moment in time, using a particular frequency band to filter the data. And actually, I think I show a slide showing that, so I'll come back to this in a moment. But the point is that he found a signature of a reset that happened with roughly a theta frequency. So about 4 times a second. It depends greatly. That number is, you know, an order of magnitude. You know, it could be, you know, double that, but not 10 times that. You know, it would be roughly theta. I think he says 3 to 7 hertz is the range that he gives. And so he's saying that the neurons are constraining each other into patterns, and that the amplitude is revealing the degree to which they bind each other and into low-grade synchrony. His interpretation is that this null spike is the onset of a phase transition in the dynamics. The frequency is not exactly the same from cycle to cycle, from sniff to sniff. There's a sniff cycle, and the sniff, and it will later find that there's a connection between the rate of sniffing and the rate at which this happens. The AM pattern is never exactly the same, and the frequency, the gamma frequency, is never exactly the same. But the null spike destroys the old pattern so that the bulb can enter this chaotic background state, which is receptive. And then when it gets the pattern, he calls that a transmitting state, because he sees a very similar pattern at the next, you know, from the bulb to the cortex. This happens in the bulb, and then the pattern is at the cortex. And the projection is divergent, convergent, which is not like, you know, in the visual system you have these parallel pathways. So the spiking pattern here at the cortex has very little to do with the spiking pattern in the bulb, but the dynamic pattern is very similar. Okay.
So, what makes them think that that the cortex, or whichever region we are talking about, will not be able to receive this state without this, without going back into that steady background activity state? I mean,
Well, he observes in the, what's making
like,
them?
For example,
You mean Freeman and colleagues when you
yeah,
say them?
yeah. So for example, let's say that the rabbit has made a sniff and it is in a state of recognizing air, and then immediately after, in the next sniff, it gets that acid that you were talking about. So how are they sure that there cannot be a state transition without having that null spike or that steady background state? There could be a possibility that the cortex or bulb can go from one state to another without going into that steady.
Each wave packet, each little gamma burst thing lasts about 1/10 of a second, about 100 milliseconds, and then it goes back to the background state. The null spike isn't when the background state begins, it's when the background state ends, I believe.
Oh, okay.
And I may have,
That could be right. I
I
mean,
could have said that wrong when the first time the first time I said it. But I looked at, it's been about 1.5 years, but I got online with Joshua, and he showed me videos of the color plot. He showed me videos of them evolving in time, and he tried to teach me how to identify, I mean, we had to look at them at different bands, alpha, delta, gamma, theta, or beta, and then there were different conditions, and then there are different ways to look at the videos, and that they were swirling patterns of color. And he would narrate and tell me what was happening. It was a little bit of a problem because there was a time lag with the Adobe Connect. It would have been a lot better if he had been in person. So I don't think I really got the gist. He really wanted me, he actually wants to train the whole world to recognize these patterns. He's very, very fun to work with. He's very enthusiastic. I think I would need to really get what he was trying to teach me. I would need to. He encouraged me to go to Robert Kozma with it, and I haven't yet done so. Robert's a little harder. Is very busy. Not that Joshua isn't, but anyway. Did I went off on a rabbit hole there. What was the original question?
I'm just, I don't have, like you said that the background noise activity level is needed for the next state to occur. I'm not sure if that,
I don't know where you're getting the idea of needing it. What happened was Freeman had, my idea of it is that Freeman had an intuition about the connection between his data and self-organizing dynamics. And in order for him to make that connection, he hypothesized. I'm doing and then looked for this null spike and found it. That's my interpretation of it.
Okay.
So as to why it needs to be there, can't claim to fully understand that.
Okay.
But it's my interpretation that there were several. There's a very nice in Neuron. There's a very nice tribute from January of this year by Robert Kozma and Leslie Kay, who is one of Freeman's graduate students who's at University of Chicago, and it's kind of a biographical, but it contains. I can guess that there are certain parts. I think Robert wrote this part, but it's very informative about Freeman's theory and his thought process, and it's 3 pages long. It's really, and it has the biographical. It weaves in biographical information with summaries of his contributions and how his ideas juxtapose with those of the mainstream. And so it's a very nicely written tribute. And that's, I think, where I've got this idea, which could be wrong. Please understand that my concepts regarding Freeman are evolving. And if you find out anything now or later, or hear from somebody who does, I welcome feedback. But that's what I think he said.
And I've talked to Joshua before, and I've talked to some other people related to this research, and I understand that what you're saying seems to be correct or jives with what I've heard before.
I specifically remember in that tribute them saying that he made several predictions from his models, his mathematical models, of phenomena that were like 20 or 30 years discovered. And one of them in particular, and I'm not remembering the specifics, but one of them in particular, like the olfactory community found the idea laughable. And in 20 or 30 years, there was a set of researchers who revealed this possibility, and then a confirmation. And I don't remember the specifics, but I find that to be a pretty neat kind of feature of his story or of his work. And I think I could have gotten that mixed up as far as the null spike and how he thought it up. But I've read a lot in the last 10 days. And I've tried to keep it straight, but it's still a little jumbled. Sandy, you look like... Okay.
Go on with it.
Okay. All right. So this is a schematic from Scholarpedia, which is the Scholarpedia article written by Freeman and Kozma is very nice. It's on Freeman's mass action is the name of the article. And it talks about some of the latter methods that were used. The reason I put this slide up here is that there's a process by which he looks at the overall frequency spectrum, and there's one spectrum that's over a 0.1 second window, and that's the one that goes mostly straight and then
I'm
down.
not sure what you're pointing to at all.
Top left. Okay, this is a power spectral density plot. Log frequency is on the x-axis and power is on, log power is on.
Frequency of,
Okay, do you know what a power spectral density, how it's calculated? You take a signal, a complex time series, and then you analyze it in, the most common one is a Fourier method. It's a transform that takes a time series and then gives you a frequency representation of the time series. So there's a transform from what's known as time space to frequency space. And so the idea is that any frequency can be decomposed into a linear combination of sine waves of different frequencies. And you can do this discretely and you get the Fourier series, or you can do it continuously, in which case you get the transform. So your basis states are either, the integral multiples of cosine x, cosine 2 pi x, cosine 4 pi x, etc. That's the series. Or you can have an integral rather than a series representation, a series summation with a continuous. And it's a way of representing the signal in a different space, frequency space. So the idea is that the graph represents the frequency content. If you had a pure sine wave, it would be a spike at the appropriate frequency. Or a Dirac delta function, I believe it's called, which is like a Gaussian with the standard deviation approaching the limit in a limit of 0. And it basically has an integral of 1 in an interval that contains it, and an integral of 0 in any other interval. The power spectral density that you get depends on the length of the time window over which you calculate it. So for a 6-second window, you get a good idea, you get high frequency resolution but low time resolution. Okay, because you're going over 6 seconds, but it gives you a very good idea of the frequency content of those 6 seconds. How much of each frequency content, what the power is. And the power is related to the square of the amplitude.
what's the signal that you started with?
Well, in this case, it's an average signal over 62 of the 64 channels.
Signal of what?
Electrodes.
The electrodes on the brain. Okay, and so the long time window gives you tells you what the frequency breakdown is. The short time window is going to be more specific to the time, and so he looks at both of them to find a peak.
Time of what?
The time of the activity that you're studying.
So, a SNP, for example.
Well, you want to study how the neural activity how it changes over time in relation to such an event as a SNP. And if you want to understand the frequency, this is.
So you pick the time arbitrarily. You pick it yourself.
Well, he steps through different times with this analysis, and will do this. He will take a 0.1 second window and do an analysis over each one of those to see what's happening within this. But with this top left is to determine a frequency around which to filter. So he finds a peak in the gamma range. In this case, I think 22 is the peak for this one, and 20 to 25 is what it says over there.
20 to 25 what?
Hertz. And then when he filters at that frequency,
Oh, I see it.
B is the lower left. That's what the signal looks like when it's filtered at that frequency. So let's say there's some other things happening inside. What he's trying to do, this is like focusing. This is like tuning a radio in a field in which you have lots of different signals at different frequencies, you know, doing different things. Maybe some of them are noise from stars. Maybe some of them is noise from I just moved my hand and maybe I've got some charge on my hand, and that might make a radio that's not grounded well. It might make it, you know, oscillate. But if you have a good tuner that acts as a filter to filter out things that are not at the frequency of interest, then you can, you recognize the static from, hey, that sounds like it might be somebody talking. So this looks like a theta gamma pattern in the bottom left, or a cross frequency coupled. You've got and so he's tuning, he's filtering through this, looking for this, and that's the mathematical approach that he uses. Okay, now.
So he filtered for 20-25 hertz, but he is finding another frequency within that. Is that?
Well, he's finding a beat frequency, and it corresponds really to the, if you look at the long, it's hard to describe. Can you see my mouse pointer?
Yeah.
Okay, there's this smoother line that comes straight across and then drops down, and then there's a very jagged line that has this linear regression line in it. Okay, this jagged line has a peak that is similar to the one for the 0.1 second line, which is the time window that he's looking at. But there's an earlier peak that's much higher, and it's going to be in the theta range.
Okay.
So that's probably what this beat frequency is.
Okay.
Okay? Now, so with this same filter, okay, this is just the filtered signal, and the Hilbert transform takes that and decomposes it into complex variables somehow. It's called an analytic frequency and an analytic amplitude, or the square of which is a power. So he looks at the way the analytic power and analytic frequency change in time with this filter signal. Okay, you got to do a lot of filtering to get here, but here's the null spike, and here's what the analytic frequency does at the null spikes. In between the null spikes,